Okay, we talked previously about how different macronutrients like fats, proteins, carbohydrate contain energy. We said that a gram of protein can yield 4 food calories. That's a unit of energy. So where does this come from? That's what we're going to look at here. And two big facts to understanding what is the origin of energy production as it relates to chemical bonds. First of all, whenever we break a bond, it requires energy. Whenever we form a new bond, it releases energy. And this is important to remember because it can seem like bonds are like savings accounts, right? Where you put energy into a bond and you get it out later. But it's actually a little bit more nuanced than that. The reason that you're able to harvest energy is because we're taking bonds, which are semi-stable, or not even semi-stable, they're stable bonds, but we can form more stable bonds. And because we're going from something that's stable to something that's even more stable, we get energy. This is kind of like the ball sitting on the table falling off. It's not like the ball is unstable when it's sitting on the table. But if you should give the ball a pathway to fall off the table into the floor, it will do so, giving you energy in the process. Things want to find an even more stable state than they began with, and when they do that, energy is formed not because the bonds themselves contain energy, but because weaker bonds are breaking and even stronger bonds are forming to give you a net gain. And here's a breakdown of this idea. We start with reactants on the left side, and we're going to see that energy is plotted on the y-axis. So the higher something appears, the more energy it has. And as we go from left to right, tracking this curve, this is basically the progress of reactants becoming products. And we're going to clarify these terms a little bit more soon. Reactants are our starting materials in a chemical reaction, and a product is our ending materials in a chemical reaction. And this is really, really important to consider. When we see chemical reactions written out, which we're going to see soon, it's not just a bunch of letters and numbers on a page. It's a bunch of stuff that we begin with, the reactants, and the results of what happens after they engage in this chemical reaction, the product. And so when we look at this, we say reactants and products, right? Reactants start kind of midway up the energy. It takes a little bit to get the reaction going. This is common for all reactions. And then products end up lower on this graph. So which of these has more stable bonds? Go ahead and pause for a second and see if you can answer. Do the reactants or the products have more stable bonds? All right, hopefully you're able to answer. It's the products. Products are lower in energy. Therefore, the products contain more stable bonds. Again, we break the less stable bonds of the reactants. That takes some energy. And then we form even more stable bonds, getting back all of that energy that we put in the first place and more. When the products have more stable bonds than the reactants, we end up having energy come out of the reaction. And we saw this in previous chapters where when we have really stable things that are formed, those tend to be the products of energy-giving reactions. Okay, we want to classify these reactions. If more energy is needed to break the bonds than is released, it's endothermic, right? If we put more in than we get out, that means it requires energy. We call that endothermic, taking in energy. If more energy is released than it takes to break the bonds, that's what we saw previously, we call that exothermic. Energy comes out. We get out more than we put in. And these terms are really important. Endothermic means it requires energy, generally in the form of heat, to move forward. Exothermic means it produces energy, generally in the form of heat, when that reaction occurs. And so we have a few examples from nursing where we have endothermic or exothermic reactions shown. Here's a cold bath. This contains solid ammonium nitrate. And so we have these in separate compartments from water. This only occurs when the water is added to the chemical. So within this pack, we have the sealed up solid ammonium nitrate. Once we break that by cracking the cold pack and the water hydrates the ammonium nitrate, then the process occurs. Dissolution of the ammonium is endothermic, and we show this reaction here. NH4NO3 solid becomes NH4 plus and NO3 minus. This is the dissolution process that we've seen before, and this is how we show that in a chemical reaction. The solid compound becomes the two polyatomic ions, aqueous. This is showing how water will dissolve this compound. And we see here delta H is greater than 0. That means it requires energy. It's endothermic, that the bonds, the H is another way of showing the amount of energy in the bonds, it's greater than 0. The products have more energy than the reactants. We have to put in more energy than we get out from breaking the reactant bonds. That's how this particular one works. A hot pack is an exothermic reaction. It produces heat. And here we have pretty much the same basic setup. We have the ingredients for this reaction that are separated by something that's broken. And when they're allowed to come together, this reaction occurs through crystallization in this case, and the process releases heat, delta H less than 0. And we do want to commit these to our knowledge, right? That delta H less than 0, H is basically energy here. It's denoted as enthalpy, not energy. It's a bit beyond the scope of the course what that kind of means, but it's basically the energy. This says the energy change is less than 0. If the chemicals are losing energy, heat must be released. This is what makes the pack warm. This is showing an exothermic reaction. Finally, what about burning fuel? Is burning fuel endothermic or exothermic? And before we try to put this into a chemical equation, let's just think about this generally speaking. Is this endothermic or exothermic? When you burn fuel, what happens? What do you feel come in or out of the system? I guess, how do you feel the surroundings change? Studying the surroundings is a really good way to tell what's going on to the chemicals because it's kind of opposite, right? If it feels warmer on the outside, the fuel must be giving off heat. If it feels colder, the fuel must be taking in heat. So go ahead and pause this and see what you think, endothermic or exothermic. All right, this is exothermic. It creates heat. This is a form of energy, and we can see this in the following reaction. This is natural gas, CH4, and burning this fuel requires oxygen. So O2, CH4 with two O2s becomes CO2 and H2O. And we already know this is exothermic. We know this about the reaction. And so because we already know something about this reaction, we can also conclude that these bonds are less stable than these bonds on the right. We're forming more stable bonds. Because we're forming more stable bonds, we have heat that's formed. And finally, this heat energy that's formed is going to be equal to the difference in bond energy. This is conservation of energy. It means that energy is neither created nor destroyed. While we are making more stable bonds that contain less energy, that energy can't just evaporate. It has to go somewhere. And in this particular case, in this exothermic reaction, it comes out in the form of heat.